The bad news today is that there will be quite a bit of math, but the good news is that we will only do it once, and it will only take something like half hour. There are quantities in physics which are determined uniquely by one number. Mass is one of them. Temperature is one of them. Speed is one of them. We call those scalars. There are others where you need more than one number. For instance, on a one-dimensional motion, velocity, it has a certain magnitude, that's the speed, but you also have to know whether it goes this way or that way. So there has to be a direction. Velocity is a vector, and acceleration is a vector. And today, we're going to learn how to work with these vectors. A vector has a length, and a vector has a direction, and that's why we actually represent it by an arrow. You all have seen this is a vector. Remember this? This is a vector. If you look at the vector head-on, you see a dot. If you look at the vector from behind, you see a cross. This is a vector, and that will be our representation of vectors. Imagine that I'm standing on a table in 26,100. This is the table. And I am standing, say, at point O. And I move along a straight line from O to point P. So I move like so. So that's where I am on the table, and that's where you will see me when you look from 26,100. It just so happens that someone is also going to move the table in that same amount of time from here to there. So that means that the table will have moved down, and so my point P will have moved down exactly the same way. And so you will see me now at point S. You will see me at point S in 26,100, although I'm still standing at the same location on the table. The table has moved. This is now the position of the table. See, the whole table has shifted. Now, if these two motions take place simultaneously, then what you will see from where you're sitting, you will see me move in 26,100 from O straight line to S. And this holds the secret behind the adding of vectors. We say here that the vector OS, we put an arrow over it, is the vector OP with an arrow over it plus PS. This defines how we add vectors. There are various ways that you can add vectors. Suppose I have here a vector A, and I have here a vector B. Then you can do it this way, which I call the head-tail technique. I take B, and I bring it to the head of A. So this is B. This is a vector. And then the net result is A plus B. This vector C equals A plus B. That's one way of doing it. Doesn't matter whether you take B, the tail of B to the head of A, or whether you take the tail of A and bring it to the head of B. You will get the same result. There's another way you can do it, and I call that the parallelogram method. Here you have A. You bring the two tails together. So here is B now. So the tails are touching, and now you complete this parallelogram. And now this vector C is the same sum vector that you have here, whichever way you prefer. You see immediately that A plus B is the same as B plus A. There is no difference. What is the meaning of a negative vector? Well, A minus A equals 0. Vector A subtract vector A equals 0. So here is vector A. So which vector do I have to add to get 0? I have to add minus a. Well, if you use the head-tail technique, if this is a, you have to add this vector to have 0. So this is minus a, and so minus a is nothing but the same as a, but flipped over 180 degrees. We will use that very often. And that brings us to the point of subtraction of vectors. How do we subtract vectors? So a minus b equals c. Here we have vector a, and here we have, let me write this down here, and here we have vector b. One way to look at this is the following. You can say a minus b is a plus minus b. And we know how to add vectors, and we know what minus b is. Minus b is the same vector, but flipped over. So we put here minus b, and so this vector now here equals a minus b. This vector c is a minus b. And of course you can do it in different ways. You can also think of it as a plus, as c plus b is a. Right? You can say, you can bring this to the other side. You can say c plus b is a. C plus b is a. In other words, which vector do I have to add to b to get a? And then you have the parallelogram technique again. There are many ways you can do it. The head-tail technique is perhaps the easiest and the safest. So you can add countless number of vectors, one plus the other, the next one, and you finally have the sum of 5 or 6 or 7 vectors, which then can be represented by only one. When you add scalars, for instance 5 and 4, then there's only one answer, that is 9. 5 plus 4 is 9. Suppose you have two vectors. You have no information on their direction, but you do know that the magnitude of one is 4 and the magnitude of the other is 5. That's all you know. Then the magnitude of the sum vector could be 9 if they are both in the same direction. That's the maximum. Or it could be 1 if they're in opposite direction. So then you have a whole range of possibilities because you do not know the direction. So the adding and the subtraction of vectors is way more complicated than just scalars. As we have seen that the sum of vectors can be represented by one vector, equally can we take one vector and we can replace it by the sum of others, and we call that decomposition of a vector. And that's going to be very important in 801, and I want you to follow this therefore quite closely. I have a vector which is in three-dimensional space. This is my z-axis. This is my x-axis, y-axis, and z-axis. This is the origin O, and here is a point P, and I have a vector OP. That's the vector. And what I do now, I project this vector onto the three axes, x, y, and z. So there we go. Each one has so its own method of doing this. There we are. I call this vector vector A. Let this angle be theta, and this angle be phi. Notice that the projection of A on the y-axis has here a number which I call A of y. This number is A of x, and this number here is A of z. Simply the projection of that vector onto the three axes. We now introduce what we call unit vectors. Unit vectors are always pointing in the direction of the